Welcome back everyone. In the last session, we explored the basics of classes and objects. We have seen how data and behaviors come together to represent the real world entities. So today we will build that foundation by looking how objects actually come to life in memory and how they are initialized and how they eventually get cleaned up. So this lecture is all about constructors, destructors and the object lifecycle, three core ideas that basically make object-oriented programming in C++ both powerful and reliable. We will also look at what happens under the hood when the objects are created on the stack and heap, and how we can use pointers to manage them dynamically. Here is a quick overview of what we will cover today. We will start by revisiting the object lifecycle, that is how they are created, how they exist in memory and are eventually destroyed. Then we will explore constructors, the special member function that automatically initializes objects when they are created. We will learn both about default and parameterized constructors and how they differ. Next we will discuss destructors. That is an equally important concept that is often used to handle the cleanup task when an object goes out of scope or maybe when it is explicitly deleted. After that, we will connect this theory to memory management, comparing how objects behave when created on stack versus the heap, and why that matters for the performance and safety. Finally, we will introduce pointers and objects, showing how to create and manage objects dynamically using that new and delete operations in C++. So by the end of this lecture, you will have a complete picture of how C++ handles object construction, its destruction, and how its lifetime is managed. Before we dive into code, let's understand what a constructor actually is and why it is so important. So in C++, every time we create an object, we want the object to start its life properly. Think about real-world objects. When a car is manufactured, it comes with certain default settings like fuel type, color, maybe basic configuration before anyone drives it. Similarly, in programming, we do not want objects to born empty or uninitialized. That's where the role of constructors come in. Constructor is a special member function inside a class that has the same name as a class and has no return type. You do not call it directly. The compiler basically calls it automatically when an object is created. So its main purpose is to initialize the data members of a class, in other words, to give object a valid starting value. Without constructors, we would have to write extra lines every time to manually initialize variables, for example using the setter method like setData function. That quickly becomes very repetitive and risky. If we forget one call, the object's internal data remains undefined. So by using the constructor, we automate that process. Initializing happens automatically the moment we create an object, and it ensures that every object starts its life in a predictable and consistent state. Constructors can also take arguments, allowing us to create objects with different initial values right from the start. For example, when we define a student class, one student might start with the name Alice maybe and age 20, while another may starts with the name Bob and age 22. So both can be created in a single line of code. So in summary, constructors gave us automatic, reliable and a flexible way to initialize objects. They eliminate repetitive setup code, making programs safer, and they reflect how things work in the real world. Where objects do not exist obviously in a vacuum, they are always born with certain attributes. Before I show you constructors, I want to motivate why they are useful. Rather than explaining this concept abstractly, we will look at a code. First, we will write a simple class with no constructor and initialize objects manually. Then you will see that repetitive calls and risk of uninitialized state that I discussed earlier. Then we will replace that pattern with constructors, both the default and parameterized constructors, and you will see how constructors make initialization automatic, safer and more concise. Here we have created a student object s1, but it didn't call set data function. The object exists, but its members are uninitialized. So there's a risk of garbage values, obviously inconsistent state, or forgetting to initialize entirely. So even if we always remember to call set data function, doing this everywhere is very repetitive and it is also error prone. So in larger systems, it becomes a maintenance problem. So how to fix this? We make initialization automatic by using constructors. A constructor runs the moment an object is created, guaranteeing valid initial state. So you can see in this example, class student defines two data members, name and age. Student is a default constructor with no return type, same name as the class, and it assigns safe default values to the relevant data members and it prints a message. Now in main function, we write student s1. At this exact moment, the constructor is automatically invoked and we will see the message on the console, default constructor called. Then s1.displays basically prints the initialized values. There is no chance of reading garbage or forgetting to initialize, as this constructor is called automatically by the compiler. Key takeaway is that constructors provide a safe and predictable start state for each object. Now let's see this example. This class now has the constructor that accepts parameter n and a. When we create student s1 and we pass two parameters, name and age, Alice and 20 respectively, the constructor runs immediately and sets the name and age accordingly. So there is no post creation set data call. Object creation and initialization basically happens in one atomic step. So this avoid mistakes and make the code clearer about the required data at a certain time. Constructors cannot have a return type. They are not regular member functions you call directly. They are basically invoked by object creation syntax. You can, however, overload constructors, define both the default and parameterized one to provide multiple ways to create object. For example, student with maybe empty brackets and no arguments, and student with some arguments like some name and age. If you define no constructors, the compiler supplies a default one only if no constructors are defined. But as soon as you write any constructor, the compiler no longer auto-generates the default one. Now let's look at a simple real-world inspired example, a counter class. Imagine we are keeping track of number of customers entertained during each hour in a service counter, says from 8 a.m. to 12 p.m. So for this duration, we want a small program that can count how many customers have been served in each time slot. So here is a simple class name counter. Let's walk through this code step by step. Inside our class, we have a private data member called count. Making it private ensures that it cannot be modified directly from outside the class, so this protects the internal state of data. Then we have two public member functions, inc_count, which increases the count by 1, and get_count, which returns the current count value. Now let's see how this class is used in our main function. In main function, we create an object called slot1. Think of slot1 as representing some time slot, for example 8 a.m. to 9 a.m. hour. When the first customer is served, we call slot1.inc_count. This basically increases the internal count by 1. Then using the function get_count, we print the number of customers served so far, which should display 1 by this time. Notice something very important here. The internal variable count is private, meaning that no one outside the class can just change it to any random value. The only way to modify it is through the function inc_count, and that's basically encapsulation, controlling access to data through well-defined interfaces. But there is a problem here. The count variable was never initialized. In C++, local variables are not automatically set to 0. So before we start counting, we should make sure that count starts from 0. That's exactly where the constructors help us. In the next example, we will add a constructor that automatically initializes count to 0 when we create an object. So every counter starts at 0 by default. So let's see the next example. In our previous version of counter class, we had a small issue that variable count was never initialized. So we fixed that problem by introducing a constructor. So we added a special function named counter, and notice it has the same name as a class and it has no return type. So this is basically your constructor. And this function automatically gets called the moment we try to create an object of a counter class. Inside the constructor, we set count is equals to 0. So now every time we create a counter object, like in main function counter slot 1, it automatically calls the constructor and it starts with the count of 0. When we run this code, the first thing printed is counter initialized to 0. That's because the constructor executes as soon as the object slot 1 is created, before any other code in the main runs. Then we call the function inc_count twice. Each time the count increases by 1. So finally, when we display the count using slot1.get_count, it prints customer served as 2. That's exactly what we expect. So what did the constructor achieve? It removed the risk of uninitialized data, and it guaranteed that every counter object starts in a known state, ready to use state. And it eliminated the repetitive setup code in main. This is one of the most important role of constructor, which is automatic and reliable initialization of objects. Now imagine we had multiple counters for each hour, for example 8 to 9 am slot, then 9 to 10 am slot, 10 am to 11 am slot, and so on. So with constructors, each one starts cleanly at 0 without us writing a single extra line of setup code every time for each slot. So constructors give us a safe and automatic way to initialize objects. They eliminate repeated setup code, and this reduces bugs from maybe uninitialized data. Next, we will look at destructors, the counterpart that handles the object cleanup. In the last section, we saw how the constructors help us to automatically initialize objects when they are created. Now let's look at the other end of the object's life cycle, which is when an object is no longer needed. For example, when an object goes out of scope, for example at the end of a function or a program, C++ automatically calls another function called destructor. So when an object goes out of scope, for example at the end of the function or a program, C++ automatically calls another special function, that is destructor. And destructor's job is to clean up, to release any resources the object was using, such as memory, file handles, or maybe network connections. Just like a constructor, a destructor has the same name as a class, but it starts with a tilde symbol and it takes no arguments and returns nothing. So in our class, counter class, you see a destructor named as counter, and inside we simply print a message showing the final count before the object is destroyed. When the program starts, the constructor runs automatically, initializing the counter to 0. Then we increment the count twice and display the value using getter function get_count, which shows 2. Now notice that we didn't explicitly call any destructor, but when the main function ends, the object slot 1 goes out of scope. At that exact moment, the destructor is automatically called, printing the relevant message that we have written inside it: counter object destroyed, final count is 2. This confirms that the destructor allows us to perform any necessary cleanup automatically without needing to remember to call anything manually. In our more complex programs, destructors are crucial for memory management, especially when we dynamically allocate memory using pointers. For example, if an object opened a file and allocated a block of heap memory or a memory on heap, the destructor would make sure to release it properly when the lifetime of the object ends. So in short, constructors build and initialize objects, and destructors clean up them safely when they are no longer needed. Together they define the object life cycle from creation to their destruction. In the next part of this lecture, we will explore the life cycle in more depth, including how memory is managed when objects are created on stack and when they are created on heap, and how pointers are used to handle such cases. Now we will look at a class that allocates memory dynamically on the heap and see why destructors are essential. If we fail to free heap memory, our program leaks memory and can cause problems in long-running systems. Now before we run this example, let's take a closer look at the data members of this class. So first, notice a pointer A. It doesn't store actual numbers, it simply points to an array that lives on the heap. This array is created inside the constructor using that new keyword, new int 5. So A is like a reference or handle to that block of memory, that 5 cells block. Next we have two integer variables named size and current index, and while they sound similar, they basically track two different things. Variable size represents the number of elements currently stored in the array. For example, when the program starts, there are no values yet, so size is obviously initialized to 0. Every time we successfully add a new element, size increases by 1. On the other hand, current underscore index tells us where in the memory the next element should be inserted. Think of it as a moving pointer that starts at position 0 and advances each time we add a new value. So when we call add function, add 3 for the first time, current underscore index is 0, and the statement a current index plus plus is equals to n. This statement basically stores the value 3 at 0 index, then increments current index to 1. At the same time, size becomes also 1, meaning now we have one valid element in the array. Now let's walk inside the constructor. Inside dynarray, we call new int 5. This basically allocates an array of 5 integers on the heap because we have used the keyword new. The constructor fills it with 0 and prints a message so we can see it when it runs. Notice there that our class now owns that resource. Because the class allocated memory with new keyword, someone must eventually call delete operation on that pointer. If we never call delete operation, the memory remains allocated until the program ends, and that's a memory leak. In short programs, this may be harmless, but in real servers or long procedures or long processes, it is disastrous. To solve this, we add a destructor with the same name as a class, and the destructors execute automatically when the object is destroyed and performs delete operation. So this delete A operation is performed. So in our code, it also prints a message so we can observe the life cycle. Now let's look at the inner block in main. So when the block ends, ARR, that or dynamic array, goes out of scope. The compiler calls its destructor automatically and delete operation or command basically runs. You should see dynamic array or dynarray destroyed message right after we exit the block. That basically demonstrates stack allocated automatic objects that are constructors at creation and destructors at scope exit. So two important notes here. After delete, you should avoid using the pointer again or set it to maybe null pointer to prevent undefined behavior. Next, our class manages a raw pointer. If we let the compiler generate the default copy constructor and copy assignment operator, copies will copy the pointer value, leading to two objects owning the same heap block and causing double deletes or corrupted memory. So you must consider implementing copy constructor and a copy assignment operator and a destructor for sure. So in short, Destructors are the correct place to free resources that a class acquires, either it's a memory or a file or a socket. So for dynarray class, the destructor ensures the heap array is freed when the object's lifetime ends, whether the object was automatically allocated on stack or explicitly deleted after new. So in short, destructors are the correct place to free resources that a class acquires, either as a file or a memory. So far we have seen how constructors and destructors define life cycle of an object, that is creation and cleanup. Now we will explore where in memory those objects actually live and how that affects their behavior. Specifically, we will talk about stack objects, heap objects, and the role of pointers in managing them. Have you ever wondered where your program's data actually lives while it is running? Let's talk about two places in memory, the stack and heap. First, the stack. Think of a stack as a pile of plates. Each time a function is called, a new plate is added on the top. This plate holds the local variables, function parameters, or the return addresses. When the function finishes, the plate is simply removed faster, in a cleaner and automatic way. Because of this, stack memory is very fast but also limited in size. If you use too much of it, like creating a huge local array or calling functions too deeply, you will hit stack overflow. When you create an object like counter C inside a function, it is stored on a stack. That means it is created when the function begins and destroyed automatically when the function ends. No need for manual cleanup. Now let's move to the heap. Heap is a large pool of memory used for dynamic allocation, which is the memory you request at runtime using something like new or malloc commands in C. Unlike stack, heap memory doesn't go away automatically. You as a programmer are responsible for managing it, which means you must free it when you are done. If you forget, the memory stays allocated, and this causes a memory leak. So heap is more flexible, perfect for the data that needs to be live beyond a single function, but is also slower and more prone to fragmentation. But when you use a new keyword like counter static p is equals to new counter, the object is created on the heap, which is a large pool of memory managed by the program. You control exactly when a object is destroyed, calling a delete function or delete command. So this difference is crucial. Stack objects have automatic lifetime, however heap objects have manual lifetime. In languages like Python or Java, the garbage collector automatically handles the heap memory for you, but understanding these concepts is still crucial for efficient programming. Here we see two objects of the same class, one created on the stack and one on the heap. The first line, demo stack obj, creates a stack object. It runs automatically the constructor, and when main ends, the destructor runs automatically. The second, created with new demo, new keyword, creates a heap object. The constructors also runs immediately, but notice here it won't be destroyed automatically. We must explicitly call delete heap object to reallocate the memory. If we forget that delete command, the destructor never runs and we may leak that memory. This is why constructors are essential for dynamic memory management. When we create objects dynamically, we interact with them through pointers. A pointer is a variable that stores the address of an object in memory. That arrow operation, that hyphen and greater than operator basically, is a shorthand for accessing members through a pointer. It is equivalent to static p dot method command or line, but much a cleaner and readable notation. So for heap objects, we typically use this operator, while for stack objects, we use dot operator. Now let's visualize how the pointer to an object works, because this concept underpins everything related to dynamic memory management. Let's walk through this example carefully to see what's really happening in the memory. First, we define a class box with one data member, length, and a method showLength. In main function, we create an object b1 of box on the stack and initialize it with value 10. Next, we declare a pointer box static ptr. This pointer variable itself also has a memory address, say the address ending with ef4. But right now it doesn't point to anything, it just contains a garbage. Then we assign ptr is the address of b1 basically. Ampersand sign and b1 operator gives us the address of object b1, which is the address ending with f08, and that gets inside ptr. So ptr now holds the value at address ending with f08, which means it's pointing to the memory location where b1 resides. Now when we call ptr, that arrow operator, to show length, that means go to the address stored in ptr, find the object there and run its show length function. Now inside the function it prints length is equals to 10 to the console. So notice both the addresses are the same. That confirms ptr is indeed pointing to the object b1. That brings us to the end of this lecture on constructors, destructors and object lifecycle. Thank you for your attention and participation. In our next lecture, we will move one step further, exploring how functions and objects interact. We will learn how to pass objects to function, return them, and understand the difference between call by value and call by reference and object composition. This is where we will really see how objects start to collaborate with each other to perform complex tasks. So I'll see you in the next session.